Yeah, you all have been very busy all these days. So now we are going to now discuss one topic which we have just started few months back, where we have initially started with structural dynamics, the basic principles, and the uh, problem of determining natural frequency of vibration and things like that. Our primary aim, of course, as a civil engineer is to carry out the seismic analysis of buildings subjected to ground motion. And as I see that of late you all have been involved in big way in carrying out the seismic analysis of buildings, or in some way to account for the seismic movements and things like that. While I think for many years you were always saying that our PT is only for dead plus live, and seismic and all is consultants problem. So you were safely away from the seismic analysis, and you had no worry at all as to how to take care of the seismic disturbance and things like that. But now I think you are getting involved, and that is good in a way, because as an engineer it is better that you understand properly the seismic behavior of buildings and provide for the disturbance and things like that. Now, seismic analysis, as you have all seen, some of you at least, that you are using extensively the provisions of the IS code 1893, the code that you have been referring to. Now, this seismic analysis that we do is based on two codes that we use. One is 1893, which was revised lastly in 2016 for earthquake resistant design, and there is one more code 13920, which is for ductile detailing, which gives a lot of provisions to ensure that under severe earthquake the structure will perform satisfactorily without damage or without collapse, and so. Now when you consider 1893, this 1893 for many years, 1893 was a code where only one code was there for this number. While of late they have now bifurcated it into 5 parts, out of which of course we are more concerned with only part 1, which is a seismic code for buildings. But there are other 4 parts. Out of that, liquid retaining structure or water tank is a code for that, part 2. Bridges and retaining wall is for part 3, and for industrial structures including chimneys and stones, stack like, so that is part 4. For dams and embankment, they are indicated that it will be brought out, but it is not yet done. While earlier all these structures were covered under one code only. Now because of the input that they have received from industry, and because of the special features associated with them, they have now divided it into 5 parts. While IS 13920 is for ductile detailing, that is once you design the main reinforcement for any structure, for columns, beams and so on, then you have to provide some additional details in those elements, so that under severe earthquake the structure will perform satisfactorily to the extent that it will not lead to collapse of the structure. Because what we do in seismic analysis is that our structure would remain elastic for those design loads. Now that design load is calculated with a factor R, which we will see later on, called as response reduction factor, and we use factor as high as 5 in some cases. That means our seismic forces are reduced to that extent. 20% force is only applied if you use a R equal to 5, and for that force we ensure that the structure is safe. But under severe earthquake that is not going to happen. The forces will be very large. Our structure is expected to remain elastic for that value of R, but real earthquakes are much severe in worst of the situations. At that time, though our structure is not going to remain elastic, we don't want it to collapse. So we are providing some details in the structural elements, so that though it doesn't remain elastic, it may lead to yielding of steel, or it may lead to cracking of concrete and so on and so forth. It may need major repairs, but doesn't matter. It will not lead to collapse. So the loss of life is avoided. So the whole idea in using the provisions of 13920 is that the collapse under severe earthquake is avoided, while 1392 this 1893 only ensures that for that design load the structure remains elastic. So okay, that is the major difference in the two. Now in IS 1893 they are covering few of these provisions, that is general design criteria and the principles of design are briefly outlined. Then they have classified buildings into regular and irregular configurations, and for irregular configuration they have indicated what special provisions are to be made in the design. Then how to calculate seismic force for a given building, so that they have given some simple formulae and the concept involved in it. There are two methods which they have indicated. One is the equivalent static method, which is to be used in certain class of buildings, and dynamic analysis method including time history method or the response spectrum method. So that is used for most of the buildings which we come across. Only for buildings 15 meter in height and less, and that too also regular buildings, you can go for equivalent static method, but for otherwise you have to consider at least the response spectrum method and so on. Now when you consider the ground motion as a cause of earthquake, then we say that the ground motion at a point depends upon few of these parameters. That is, one is the magnitude of earthquake, which you must have seen a Richter scale is one scale which is used for designating the magnitude of earthquake. Richter scale, the highest value is 10, while otherwise it ranges between 4, 5, 6 and so on. If it is very low like 2 or 3, then you may not notice and building may not suffer in general much of the configuration damage. Then the earthquake, that ground motion which is felt at a point, depends upon the depth of the focus, that is the real point underneath the surface of the earth where the crack originates under the influence of ground motion, which is the continuous movement that takes place at the earth interior of earth. So at some point the stresses develop, and when those stresses exceed the load carrying capacity of the soil, then the cracks develop and sudden release of energy occurs. So the point at which that release in energy occurs called as the focus. If that focus is deep down the surface of the earth, then the effect of that earthquake is little less, while if it is a shallow earthquake, then the energy release is immediately of a very severe nature and so on. Then we have to see as to where is the focus and where is the structure. If the focus is say New Delhi and you are at Bombay, then of course nothing will happen to that. So we have to see what is the distance between the focus and the structure that you are considering. So how long it is. The earthquake has originated somewhere, but your structure, how far it is from that source. Then secondly, now that we call as the distance from epicenter. Now there is one point where the crack really starts energy release at some point below the surface of the earth. The point vertically above that on the surface of the earth, like Bhuj earthquake. So Bhuj is the point at which you have got a point on the surface of the earth, but the crack has occurred maybe 15 kilometers below that. So that is the focus where the crack has started, and point vertically above that on the surface of the earth is called as the epicenter. So we have the epicenter on the surface of the earth, while focus is the point underneath the surface. Okay. Then we see that from that point where the energy release occurs, you have got a structure, so the waves have to travel considerable distance. And in between, what type of soil is there? If that soil absorbs a lot of energy, then the effect field will be less, and vice versa. Okay. And finally, your structure is located on some strata at that point. So we have to see what kind of strata is there where you have actually founded your foundation over there. So if it is a sandy soil, okay, it may get a lot of disturbance and otherwise. Okay, so that is basically the general information about the earthquake. Then we say that the response of the structure, once you see that earthquake has hit the structure, then we say that the response of the structure depends upon these important points. One is the nature of foundation soil. So what kind of soil is there, whether it is rocky soil or whether it is sandy soil, medium, murum, and so on and so forth. So what kind of foundation soil is there at that point. Then the materials of the structure, whether it is masonry or concrete or steel, it will be dependent on that. Then form of structure, whether you have got a regular form or very irregular building, accordingly the damage will be different. Size of structure, if it is a very small structure or massive structure, accordingly the damage will be affected by that. Then you have got mode of construction, whether you have got precast construction with some joints in between, in situ joints or something like that. So that all will decide whether the response of the structure will be of a particular type or not. One more point which decides the response of the structure is the duration and characteristics of structure. So how long the earthquake has lasted, maybe 10 seconds, 20 seconds, 30 seconds, whatever it is, and what kind of waves are created. I mean, the earthquake ground motion that we see has got those ground waves traveling, and those waves have got lots of frequencies in between them. I mean, they are made up of various frequencies as you split that entire motion. So it contains various frequencies. So which frequencies are predominant in the earthquake? If your structure has got a natural frequency of vibration, let us say 1 cycle per second, or period of vibration we say 1 second, then if your ground motion also has got the same frequency, then there will be a resonant condition over there, because your ground motion is going to resonate along with the structure, and in that case the damage will be very severe. So we have to just see as to whether the frequency content of the earthquake is of what type, and whether your structure will have a severe effect of that, and so on. And lastly, of course, the dynamic characteristics of the structure. What is the frequency of vibration for your structure? Now, as far as the characteristics of the earthquake is concerned, all upper points, that is right from, you can say, the duration and characteristics of the structure. So here there is no control for us as to where it will originate, when it will originate, and what will be the distance between that source and my structure. So that is all uncertain. So we can say that we have no control on that. We have only got a structure. For that structure we have the dynamic characteristics, and what kind of earthquake is going to strike it, that is being uncertain. So we will say that we will not worry about that, let the code worry about it, and code will give you some guideline for designing your structure and so on and so forth. Okay. Now the design approach for buildings, we say we have got basically 3 different steps in the design. One, the design basis earthquake, that if there is a minor earthquake, then we say there should be no damage to my structure. Structure should continue to behave like as if there was no earthquake at all. Then we have got design basis earthquake, for which we generally design our buildings, where we say that some minor damage might occur here and there, some partition walls may collapse or may develop cracks and so on. So that is our design basis earthquake. What we do as for our design is our design basis earthquake. And lastly is the maximum considered earthquake, MCE, where major earthquake, where we say that our structure must be so designed and detailed so that the structure does not collapse under the worst of the earthquake. Okay, now that is our provision, we will say, our design concept. But under worst case, if the source of earthquake is right below your building, then of course it has no chance of survival. It is anyway going to collapse. So we don't want our structure to be designed in such a way that if the source is just below my building, still the building will survive. That will not happen. Nobody can design building for that. So we will say that that is a remote possibility. So I am not worried about that. Only I will say that if there is a major earthquake reasonably away from my structure, the source is reasonably away, then we will say that okay, my structure should survive and it should not lead to collapse. Our structure rests on some type of soil. So we will say that for certain types of soils, we need to see what is the interaction between the soil surrounding the footing and structure and the structure as such. That means there is a soil which is going to vibrate, the structure is also going to vibrate, and what kind of interaction is there between the two. So that sometime you require to take that into account. Very rarely, normally in all our applications we don't worry about that. We take our foundation to be fixed to ground. So if soil moves by some way, let us say, our foundation is also expected to move in the same way. We don't say any interaction exists between the two. Only rarely where you have got sandy soil and you have got pile foundation going deep down, then you need to consider the interaction between the structure and the soil as such. The methods of seismic analysis which we are following, basically we are considering the equivalent static method, which we will see briefly, and then second method is the dynamic analysis method. The dynamic analysis method has got three we can say options. One, you can use the response spectrum method, or the model time history method, or finally full-fledged time history method. Now these other methods, that is time history methods, are too time consuming, too complex. So generally for most of the structures with which we are concerned with, we will not be worried about the time history analysis. We will only consider response spectrum method or the equivalent static method. Okay. Now this equivalent static method gives you a seismic force, base shear as we call it, as per the provisions of the IS code. That total base shear, that is total horizontal force due to seismic disturbance, is given by a coefficient AH, as you can see over here. This AH multiplied by weight of the building. So you have to take the total weight of the building, which consists of the dead weight and some part of live load. All of that put together, that is the weight, that seismic weight as we call it over here, and AH is the horizontal coefficient which we are to calculate based on the method which is outlined over here. So we say that you have to calculate the value of AH, which is the coefficient. Weight of the building is known to us because of the data that we are already having. Okay. Now to determine the value of AH, I have to use a response spectrum which is specially made for static analysis method, that is equivalent static method. So they have given, the code has given this one response spectrum. Now this response spectrum, as you can see, it is a response spectrum for equivalent static method, where the value of SA by G, which we will see in a minute what it is, depends upon the natural period of vibration of the structure. Now the natural period of vibration, we are not doing full-fledged dynamic analysis or the response spectrum method. Accordingly, we want to calculate the value of AH depending upon the period of vibration, for which the code has given approximate formulae. This code has given different formulae for different class of buildings. So this reinforced concrete moment frame that we are considering, moment resistant frame, if you have got steel composite or moment resistant frame and steel moment resistant frame, they have given three different formulae for calculating approximately the period of vibration, where it only depends upon the height of the building, as you can see over here. So the period of vibration depends only on height and some power of that height and so on. For reinforced concrete structures with shear walls and so on, they have given slightly different formulae. Now this is 0.075 raised to h raised to 0.75 upon root AW, where AW is the walls that you are providing, reinforced concrete walls. So you have to calculate total area of the wall at first story level for the building, or otherwise it is 0.09 h upon root D, where D is the dimension of the building in that direction. Okay. So it takes into account the size of the building, length and breadth and so on, and of course the height of the building and so on. So approximate period of vibration for other buildings is given as 0.09 h upon root D and so on and so forth. And the design lateral force that you are considering, this value of, if you see the original formula which is given, where you have got this AH. Now this AH that you have got, now AH depends upon, as you can see now, AH is given by ZI upon 2R multiplied by SA upon G. This is the formula given in the code itself, where Z is the zone factor, that is where it is located in the country. Country is divided into several zones. We will see the map in a minute. The I is the importance factor for the structure which again code has defined how much value of I is to be used. Then R is the response reduction factor, which again code has indicated how much value of R you should use. To that extent you are going to reduce the seismic force, and the main reinforcement that you are going to provide will be to that extent reduced, and you will have a structure designed for that seismic force. Once you get the value of AH over here, then you are going to get this basic horizontal force, total horizontal force that you are applying on the structure, and your building has got some height. So I want to know at each floor how much is the force is applied. Total I know it is 1000 kilonewton I am applying, but at each floor I want to know how much force is applied. So that they have assumed that it's a parabolic variation. So at the lowest height the force is less, as you go up the force increases, and finally they have given this formula WIHI square upon sigma WIHI square multiplied by base shear. Now this base shear multiplied by, if you consider first floor, your height of the first floor from ground maybe 3 meter, if you take 10th floor it will be 30 meters, so it will be W, the weight at that point, multiplied by 30 square. So as you go up the value increases parabolically, while the denominator is common for all, that is sigma WIHI square. So for each floor the weight multiplied by height or distance of that floor from ground, square of that. Likewise you sum up for all the floors, that is your denominator, and numerator keeps on changing for each floor. Okay, so that is your seismic force calculation for equivalent static method. Further the code has indicated that if you are using only static method, for example, then code has indicated that under static method, once you calculate the seismic force and so on, the minimum force code has indicated that you must apply this much force to for ensuring that your building is not unnecessarily put to a risk while designing the building. So code has indicated that minimum design earthquake horizontal force, you are having some period of vibration for the structure, accordingly you work out SA by G and so on. But code says that if the building is in any of these zones, then you must apply a minimum this much percent of the lateral. So that is a condition, that your building might be very flexible, very tall building, so it might have a very large period of vibration, it will vibrate very slowly. So it will give us a very small value of seismic force if you see the response spectrum. Now for response spectrum, the period of vibration is very large over here, then we will say that the seismic force is going to be extremely small. So code says that no, don't go for that, you still apply some minimum percentage of lateral force for that building and so on. Okay, now having gone that, now we consider the second method which we use in most of the occasions, and that is response spectrum method. Okay, for response spectrum method, the code has given directly an expression for calculating seismic force at a given level. Okay, at a given level, that is at ith floor and at kth mode of vibration. Now the structure has got several modes of vibrations, which we have seen earlier in dynamic analysis, that a 2-storied building will have 2 frequencies of vibration, 10-storied will have 10 frequencies of vibrations for horizontal vibrations only. Accordingly you have to work out all those frequencies of vibration, and for each frequency of vibration you are working out force at a given floor level in that mode of vibration. Okay, so for first mode I will calculate force in first floor, second floor, third floor, all floors. Second mode I will again calculate forces at all the floors, and likewise I will calculate forces at each floor in each mode of vibration. Okay, now they have given the formula for calculating the force at each floor in each mode of vibration. Okay, so you calculate for your given structure frequencies of vibration, which we will see very briefly, and then work out the seismic force per floor per mode of vibration. Okay, so they have given this coefficient AH, which we will see shortly. Then you have got the mode shape factor at that point, because you are calculating the force at that point in that mode of vibration. Then we have got this mode participation factor, which again is defined in the code itself, multiplied by weight at that floor level. So weight mode participation factor, mode shape factor, which is that phi, and of course AH, the design horizontal coefficient. All of that put together, now you are able to get seismic force at that point. Now mode participation factor, which code has defined in this way, it can be theoretically proved also when you see the entire process, but at this stage we will not go into the details of that. So this mode participation factor is given by sigma wi phi I upon sigma wi phi I square. Now this factor can be negative also, because this phi, the mode shape, it can be either positive on one side, negative on the other side. So it can be positive or negative. Accordingly, mode participation factor can be positive or negative, and so on. Okay. And the design horizontal force is given by the same expression, whether you are using static method or the response spectrum method. The value of SA upon G that you are working out, if you are going for equivalent static method, then this response spectrum you are using, while if you are going for response spectrum method, then you are using this response spectrum. So we say that code has given two response spectra, one to be used for equivalent static method, that is this response spectra, and this is to be used for the response spectrum method. Okay, the difference is very small, and that is also in the initial range. If you see that the peak now it is going at 2.5 over here, this maximum is coming at 2.5. It is flat beyond a period of vibration roughly 0.4. If you see, take this point down, at this point suppose it is about 0.4. Here for the other type of soil, that is soft soil, it may be from 0.8, and for rocky style it may be from 0.4. From that point onward, that means if the period of vibration is somewhere here, maybe 0.1 second or 0.2 second, then the value is flat, same, whether it is 0.1, 0.2, 0.3, it is the same value for SA by G. While in response spectrum method, they have given this taper and they have brought it down to roughly slightly less than 1 over here. So in the lower range only there is some change, but most of our buildings lie in this region with a period of vibration 1 second or more. So this is very rare occurrence, and we will not be much worried about that. So we say that as far as the response spectrum is concerned, you are using two different response spectra. The values are more or less the same. There is hardly any change. The peak for both of them is 2.5. Only thing is, you see these three different curves. The outermost one is for soft soil, the medium is for intermediate soil, and the lowest one is for rocky soil. Okay. So for rock, if you see any period of vibration, say 1 second is the period of vibration, the rocky strata will give lesser value of SA by G, because it is a very strong soil over there. So it will not vibrate much, not much disturbance there. It will be intact during earthquake. So it will give less seismic force. If you have got medium soil, slightly more, and if it is soft soil for the same period of vibration, means same building, if it is on rocky strata, it will have less seismic force. If it is on very soft soil, it will have more seismic force, because the ground is going to shake more. For the same earthquake, it will shake locally more, and thereby the building will be subjected to more disturbance. Accordingly, you will be able to see the effect of rocky or soft soil and so on. For importance factor, code has given 3 values. The latest revision for most of the buildings it is 1. For residential or commercial building other than those given over here, that is 1.2. And for important buildings or where there is assembly or large population is somehow stationed there, or lifeline structures like your powerhouse or dams and so on, or power generation stations and so on, or hospitals where these structures are definitely required after the earthquake when there is some casualty and so on. So all those structures have got a large importance factor 1.5. Please remember that this importance factor is the minimum you have to take. You are free to take for whatever reason. If client insists, no, I want more importance factor, okay, he will pay for that, but this is the minimum he has to apply. Anything above that is the engineer's choice or client's choice. Okay. The response reduction factor, code has given different factors with a minimum value. If you see over here is about 1.5 for load bearing masonry structure 1.5. Now this is because they are not very strong structure, masonry walls are there, so they are likely to get damaged during earthquake. In that case, no point in reducing the earthquake, because those forces of severe magnitude will always be there. So code says that don't reduce the forces by a great amount, only reduce them by a margin of 1.5. While for some structures, code says that you can this building with ductile RC structural walls and reinforced concrete special moment resistant frame, where you are taking all the provisions, that structure is properly detailed, it has got enough energy absorption capacity, under strong earthquake it will try to withstand that effect. For that you can reduce the force by a factor 5. So 20% force only you have to apply. For that your main reinforcement in column will be provided. Of course dead load, line load, everything will be there, but earthquake effect will be only 20% of the severe earthquake. And under worst condition 5 times larger force may come. For that you have to do the detailing, that is you have to provide enough energy absorption capacity that it will undergo large rotations at the joints, it will not get totally damaged over there and so. So that is your value of R. And for flat slab structures, of course, they have given a response reduction factor 3 and so on and so forth. There are some important notes for that, which we will see when we actually take the building. Now this is a you can say a map which shows the occurrence of earthquake in last maybe 100 years or so, where severe earthquakes have occurred, and they have given, if you see here, the depending on the diameter of that small circle which they have on, where they are showing that large magnitude of earthquake have occurred. So we can see that in northern India, where Kashmir or Assam or some part over there, or even in Bhuj, some large earthquakes have occurred. So this map is used to finally divide the country into zones. So we have got this zone map for India, that we have got this red color which is zone 5, and in the southern India and so on, we see that mostly as far as Bombay is concerned or Koina, it is slightly higher, but otherwise for Bombay it is zone 3, where this zone 3, and in southern India we will say large area Rajasthan and so on, it is zone 2 and so, because not many earthquakes have occurred in history and so on. So with all this condition, now we say that code has given the zone and the associated zone factor Z. For zone 2 it is 0.1, and for zone 5, where large earthquakes have occurred in past, the value is 0.36, which means compared to this zone, the seismic force, everything else remaining same, it will be 3.6 times larger for that zone, while otherwise it will be less and less. Because if you see the formula for calculating the seismic force, then we see that Z is a direct multiplier. So as soon as you get Z 0.1, okay, that force is 0.1 times of the remaining. But if it is 3.6, then it is multiplied by that. Importance factor is also corresponding to the multiplier in the numerator. So we say that if importance factor is 1.5, forces are increased by 50% and so on. If for most of the building it is 1, but for important buildings it may be 50% larger and so on. While R is the response reduction factor, which goes in the denominator. So if R is 5, you are dividing everything by 5. To that extent the force is reduced. So your AH is directly affecting the calculation of seismic force. Accordingly we say that if AH is reduced, the seismic force is reduced and so on. It is a direct multiplier for that. So we say that considering the response spectrum method and so on, we say that these factors play important role in finally getting the seismic force for a building at that particular point. Okay. Now having considered that, now we say that for any building, if it is a very tall building, then if it is 100-story building and it is vibrating both in X and Y direction, then there may be hundreds of modes for that particular building. But then code has indicated that you don't have to calculate all those higher modes. You only see that you calculate dynamic characteristics for enough number of modes, so that 90% of the seismic mass is mobilized. So they have given formulae for calculating the 90% modal mass which is mobilized during your calculation. So maybe only 10-15 modes are required for mobilizing 90% of the building that modal mass, and then we say that that is good enough for us. Okay. And for frequencies higher than 33 cycles per second, you don't have to calculate, because if you see the response spectrum, then we say that 33 second, once you see the period of the frequency, then the period of vibration is 1 upon 33, that is 0.03. So you are very close to this, so it is as if you are in this region. So anything beyond that, the factor is the same. So it doesn't matter whether you are calculating higher modes or not. For all of them, the value is going to be same, and we don't have to unnecessarily increase the numerical work and get results which are of no great consequences. Okay. I think we will now consider directly the use of ETABS for calculating the seismic force, because having got all of that, the main problem remains as to how to calculate all that. And fortunately now you don't have to do it, computer is there, the program is there, the software will do all the calculations. Only you have to properly feed the data for your buildings, and then the entire process is taken care of. The calculations as per the codes of practice is already there in the software. So those calculations will be automatically doing all the calculations, and you will be provided with the results for your structure. Okay. Now in our scheme of things, when you are going for ETABS, for example, let us say you have got a building, so it involves several steps for finally using ETABS to calculate in the end seismic forces. Okay. So first step is your model preparation, which involves geometry of the building, which involve geometry of individual sections, columns, beams, slabs, and so on. The material that you are using, okay, so maybe M30 concrete, M40, whatever you are using. So all that you have to now input to start with. Likewise, we will say that our first step will be to prepare the model, which involves material and geometric properties. These material and geometric properties, once you are giving, then the next step is to consider the loads that you are applying. So it may be dead load, live load, floor finish, all sorts of loads you are considering. Earthquake effect will be later on, I will indicate to you. And then the seismic loads and the parameters associated with seismic load, which we have seen in the formula, the zone factor, the importance factor, the response reduction factor. So all of that has to be somehow input, and then you will be giving enough information to the computer to go ahead with the calculation. As far as wind load is concerned, you have to again consider the data for wind load, that is its velocity of wind that you are considering, and some other parameters which are demanded by the software. Then you have got the support conditions. So kind of supports you are providing, whether it is fixed support or hinge support, so those details you have to give. Then you have got the member release or degradation, which we will see shortly. That for any member, because when the severe earthquake is there, then the RC member, as you know, that concrete is not very strong in carrying tensile forces. So the below the neutral axis, whatever is concrete, we say that it is going to crack. If it cracks, then of course its moment carrying capacity gets reduced, its shear capacity also gets reduced. So to that extent, we have to degrade the stiffness of the member. That for resisting the earthquake, we will say that okay, though initially it has got full strength, but during the process it is going to crack, and thereby it will have less stiffness. So we have to indicate to what extent the stiffness is reduced. And then you have got the load combinations, which are again mostly there are codal provisions, but ETABS takes care of all the default load combinations, so you don't have to worry about that. So you can use default load combinations, and they are all provided for two different categories. One is for calculating the deflection of the structure, and other is for designing the structure. Okay. So these load combinations are to, and then you have got the analysis done. So you have to now see whether the analysis is properly done or not, and then lastly you have to design the RC member for carrying those forces developed in the analysis. Okay. So we say that this is the outline of the work that you have to consider in the uh, given scheme of things. So I have got a simple building. I think it is reasonably tall, maybe 33 storied building is there. So this is a 33 storied building with about 5-6 floors with some podium, and above that it has got typical floor. So it is a reasonably tall building, maybe 108 meters or 110 meters tall, and the floor plan is like this up to podium, and the typical floor is like this. So basically initial structural scheme of things is already decided in consultation with structural engineer and architect. You decide where you want column, what size of columns, whether any restriction is there, and beams where you want to provide as per the room aligned arrangement and so on. So you provide the locations of the beams, locations of the column, the sizes of the columns you have to decide approximately, or initially you take any size. After one run you design, and if the reinforcement is too large you modify the size, redo the analysis and so on. So all of that will be considered. So for material property, now we say that you have got a simple choice for deciding the material property. So using this provision, now you can decide what kind of material you have got. So material, you have got 3-4 types of materials. One is concrete, other is structural steel if you have got concrete of different grades. Then you have got reinforcement, and if you are going for PT, then you have got the tendon also. So all of those properties are required to be defined initially. Okay. Having defined properties, then you have got the sections. So you decide which types of sections are used for beams, columns and so on. Then you have got walls of some certain thicknesses. So all those details now you are initially deciding. Later on you can always add and then decide whether you want anything more than that or so. Then you have to define the load pattern, where you are considering for different types of loads. For self-weight, we say that our dead load factor is 1, which it will calculate based on the density of the material and so on. While for wind load, you have to work out for wind load the velocity depending on the location of that particular site, and then accordingly the lateral load will be decided over there. For earthquake, you have to again select the parameters and then decide the kind of force parameter that the software demands. So for equivalent static method, we are considering this seismic force in x direction, for which you have to indicate as to what is the zone factor, what type of soil is there, for the importance factor what you are selecting, because it is going to take those parameters and directly work out the seismic force. While period of vibration, you can yourself work out using that formula, or ask the computer to work out depending upon the stiffness and so on. As far as height is concerned, you have to indicate what is the topmost story and what is the bottommost story base. Accordingly it will work out the height of the building, and response reduction factor, that also engineer has to decide whether you are using 4, 5, 3, whatever it is. Depending upon that, the entire seismic force calculation will be carried out. Okay. So these parameters are defined. As far as the response spectrum is concerned, you have to define, this is for equivalent static method. For response spectrum method, you have to select the response spectra, which is of course given in the code itself, and that ETABS directly picks up. While the other parameters like seismic zone, the importance factor, the response reduction factor, they are all to be decided for this method also, because they will be directly used for calculating the seismic force and so on. You have to consider the vibration in horizontal as well as vertical direction. So code has given certain conditions, that if these conditions are satisfied, like if you have got a very tall building, or if there are large cantilevers, or if the building is irregular, in those cases you have to consider the seismic force calculation in vertical direction. While normally we are satisfied with seismic force calculation in horizontal direction, but in certain class of buildings you need to consider vertical vibration also. Particularly for tall building, you consider both the directions, horizontal as well as vertical. Then you have got the load cases where you have already defined load patterns, so they are used to get the load cases. And lastly you have got the combinations over here and so on. Okay. Now when you are considering, for example, the plan of the building, then we see that for this plan, if you see this particular shear wall, which is in fact a lift well, for example, now there are three legs to it and they are all monolithic. While individually you have defined one wall like this, another wall like this, and third connected to that, but all of them put together you have got one structural member. They individually might attract some force, but their action is combined. The result of that is all of them constitute one pier. So we have to now label the pier as to which 3 or 2 units make one pier. Accordingly you consider the pier assignment over here. Okay, so this pier assignment is considered for that individually you select these 2-3 shear walls and say it is one pier and things like that. So they will be designed as one unit, and proper stiffness calculations are done internally. Okay. Then you have got load combinations, as I indicated that you can use default. One is for serviceability where lateral deformations are considered, and other is for design purpose. And you have to assign the supports, so you select those support points at the base and then assign whether you have got XYZ restraint and rotations in XY about XYZ axis restraint. Okay. And then stiffness degradation for this structure, you have to consider the crack nature of the reinforced concrete members. So for RC member, they are indicating that for columns you take stiffness as reduced only by 30%, because column has got less chance of cracking because it is under axial compression and bending. While for beam it is pure bending, so there is more cracking for building beam. Accordingly only 35% value is taken for stiffness and so on. Okay, then you have to assign the loads. So on slab you will assign the load UDL, on beams you will assign wall loads. So those kinds of loads are all assigned. Then for mass source you have to indicate which masses you are considering, that is partly dead load, live load, superimposed dead load, what percentage of that you are considering for dynamic analysis. So normally for live load we take 25% if it is 3 kilonewton per square meter or less, otherwise we take 50% and so on. So all these constitute our normal data. Then we have to consider later on, I think when you consider more complex buildings, then you see that you come to a conclusion that the building has got first mode in torsion. Sometimes you come across such situation where when you observe it and code has given, or particularly tall buildings are scrutinized by high-rise committees, so they insist that your first 2 modes should not be in torsion mode. So to understand what constitutes torsional mode, you need 2 points. One is where is the mass center and where is the stiffness center. So mass center is for in a given floor, there are all those loads, so there is a resultant mass, resultant load for gravity direction. And stiffness, all the columns, they have got different stiffnesses in different directions. So there is a resultant stiffness point. So you have got the point at which the stiffness of the entire building is concentrated and the point at which the entire mass is concentrated per floor, of course. If those 2 points are different, separated by some distance, then the mass is going to generate the seismic force due to vibration. So your applied force is at the mass point, your resistance is offered by stiffness, so that is at some other point. So your applied force is here but resistance is here, so the whole thing will rotate and then the rotation will take place, that resulting in torsion. to understand where is the mass point, the center of mass, and where is the stiffness center. So you have to use this particular command. If you see this particular value, I think here, calculate diaphragm center of rigidity. So that mass center it will always calculate, but rigidity if you have to consider, then you have to take each floor diaphragm, take it as rigid, and then it will calculate the center of that rigidity depending upon the columns over. So you have got columns offering rigidity in lateral resisting lateral load. The resultant lateral resistance is to be determined. The resultant inertia force location is to be ascertained by that mass center, and then you will in the end know whether they are close to each other or whether they are far separated from each other. If they are separated from each other by considerable distance, then you have to keep on changing the stiffnesses, because mass you cannot change. Mass is already there, it is going to remain like that. But your stiffness you can change. You can change some columns, their sizes can be changed, some columns can be added. All of that permutation combination you can do, so that the 2 points are brought closer and closer, and when they are reasonably close, then we will say that the torsion will be avoided and so on. Okay. So this is now the some substance of preparation of data. Now once you feed this data for the given building, like this building, then you get results after the entire execution is done. The first thing you should see is this center of mass and center of rigidity. So here you can see, okay. Now this XCM that you see, XCM or YCM, is your center of mass. So you are able to get this center of mass over here, and if you see here XCR and YCR, that is the center of rigidity. So you have got 2 points per floor. One where the mass is having its resultant, that is center of mass. Other is where the stiffnesses are concentrated, that is center of rigidity. If these 2 points, for example, if you see over here, this mass center X coordinate is 25.854. If you see this point, okay. So if you see, it is 25.864 and here it is 25.903. So very small distance, second digit or so on, there is a small difference. So you see that they are very close to each other, so this building is not in torsion. If that distance is very large, then you will see that the building will show in the first mode of vibration that the whole thing is turning in plan and so on. So that way you will be able to get the position of center of mass and center of rigidity. Okay. Having considered that, then for the given building you are considering the period of vibration and the so this period of vibration for the given building is now indicated in one table, natural periods of vibration and the direction of vibration. So here you can see that first mode of vibration, if you see over here, the period of vibration is 5.2 seconds, where in x direction the percentage or the component is 0.67. 1 is the highest value, while other values are corresponding to its contribution. If you see second mode, then we see that second mode has got a large contribution in y direction, so it is going to vibrate in y direction. The third one, if you see, that is in torsion. Over here if you see, the contribution is 0.5, while other contributions are less. So when you later on see the vibration of the building, that time you will see that in first case it is vibrating first mode in x direction, second mode it is vibrating in y direction, while third one is in torsion. So the main criteria for vibration is to be seen in this particular way. Okay. Later on it also gives the storey shear. Okay. For each floor it will give how much is the seismic force applied and the shear force that is all the forces above that, they are all added, and you are able to get the seismic force per floor. Okay. So this is story shear under seismic conditions. So here you can see Vx, the seismic force in y direction, and this is in y direction. This is Vx and Vy, I think. Okay. So it is able to give you the seismic force per floor. So that is all calculated as per the formula that we have seen. The next table that you get in the output is the story stiffness floor wise. Now let us see why it is calculated and what is the purpose of that. Now generally you will see that you have got columns which keep on increasing the sizes as you go down. So as you go down, the floor stiffness should increase because you have got columns of larger and larger size as you go down. Sometimes what happens, for some reason, you have got columns which are of reduced size in lower floors. You have got more number of columns, but columns are of reduced size. Or sometimes your walls are there in all the floors, but in lower few floors where you have got parking and so on, there are no walls at all. So your stiffness, if you consider walls, then the stiffnesses are high in upper floor, and in lower floor the stiffness is less. Now such floors where the stiffness of a floor is larger than a stiffness of a floor below that, there that floor below that is called as a soft story. This floor is a soft story. Now this soft story is very dangerous for any building, because you have a large stiffness above, it is going to attract a lot of force, but as you go down, the force is going to increase, but your stiffness is reducing. In that case, there is a serious situation over there. So code says that if this situation arises due to whatever reason, functionally or architect wants no walls there, or he wants to reduce size in some floor for whatever reason, as a structural engineer we have very little control on that. So we say that okay, if sizes is to be reduced and load is increased, so you put more reinforcement there, use richer mix and so on, do whatever it is, but you provide a safe structure. In that case, code says that if it is a soft stool where the floor above is stiffer than the floor below, then at that point you have to apply the forces for designing that soft story 2.5 times larger than the forces calculated normally. So you have got some seismic force, some seismic moment. If it is a soft story, then you increase that seismic force. Don't increase dead load or live load, that is same. But your seismic force must be increased 2.5 times because of the local transition which is occurring. So there you have to apply the forces 2.5 times of the normal calculated as per the software. For soft story you increase it by that margin. Now to understand whether a floor is a soft story or not, you have to calculate the floor stiffness. So fortunately you don't have to do it, ETABS is doing that. So ETABS is going to give you ready-made. Only you have to understand, oh, this lower floor has got lesser stiffness than the floor above. So that is very simple. So once you realize, oh, this is a soft story, so you design forces are to be considered 2.5 times increased seismic force and the gravity loads as they are, and accordingly you are considering the design of the elements. Now as far as displacement of the structure is concerned, when you have got a tall building, there is a limit on deflection. Then your deflection should be limited to h by 250 or h by 400, whatever it is. So code gives you this information that per floor it will give you the deflection. Over here you can see in x direction this deflection is about 176 millimeter and so on and so forth. So if you see this at terrace level, so you are able to get this deflection 0.176 meters. So that is the deflection under earthquake in x direction and so. So this deflection is already calculated in the software itself. So you have to only see whether it is in limit. If it is not in limit, then of course you have to check whether the building is to be stiffened or something like that. Then when the whole building deforms, it has got two kinds of responses. One, it linearly deforms and it rotates also in torsion. Okay. The result of that is, if you take corners of the building, they don't deform equally, because one corner may go forward because of the torsion. So code has the software gives you two values of deflection. One, the deflection of the center, and two, the maximum deflection at the corner. So once you get that, then you can get the ratio of maximum deflection to average displacement. Okay. It is giving you the average displacement of the center of the diaphragm and the maximum displacement of any point in the diaphragm. Okay. Once you get that, then code has indicated that if this ratio is more than 1.5, that is maximum to average, then you conclude that the building is in torsion because it is distorting unequally, and then you design it as per the provisions of the relevant codes. If the building has got torsion, then the code has indicated that it is a irregular building, so some precautions you have to take while designing that. So to decide whether the building is in torsion or not, firstly you are checking whether first mode is in torsion or second is torsion. So that your criteria is one criteria. Second is, during deformations, is it deforming in this fashion with torsional displacement, so that the building has got you can say severe conditions under the influence of earthquake, that it is undergoing torsion, and then you have to properly provide for torsional resistance over there. Then you are getting the joint reactions, which anyway you use for designing the foundations. Sometimes you can use these joint reactions for other purpose also, as a rough check how much load you have applied and so on and so forth, whether any gross mistake has occurred anywhere. So that information can be gathered from this table of the joint reactions and so on. Then you are able to get, under earthquake condition, the acceleration of the floor diaphragm. Sometimes there are some restrictions put in the code itself, that your acceleration during earthquake is to be limited to such and such value. So this software gives you the value. You have to just check whether it is within limit or not as per the codal provision. I think our code normally doesn't give this particular condition, but there are some countries where they are specifying that apart from deflection, the acceleration must also be limited to certain value, because when the actual earthquake occurs, it is not the deflection which causes the fear, but it is the acceleration. If it is accelerating very fast, then there is a fear is generated in the occupant's mind, and to limit that you have to see that the acceleration is limited. If deflection is gradual, even if it deflates by 1 meter, no one will notice it. But if the acceleration is very fast, then it is suddenly a very serious situation. Like when you go in a car, then if car is going at 100 km per hour, you will not notice. But if someone starts with a jerk, then you will see, hey, what are you doing? The driver doesn't know how to drive, like that, because he starts very fast. Or if a brake is applied, suddenly there is a large deceleration, and then you fall down or something happens. So that is the large acceleration or deceleration, that is very uncomfortable. So the value of acceleration is limited to that extent. Then we consider the forces in columns. Okay. The code also, you already defined these elements as columns, other elements as beams and so on. So code gives you a table of forces under different conditions. So you have got some column, then output case, whether case U1, U2, U3, all these different cases are considered, and for each of that it is giving you the axial force, the shear force in X direction, shear force in Y direction, torsion, and the moments, and so on and so forth. So this simple table is prepared. So from this you get an idea as to how the forces are changing and so on and so forth. In case you want to do some manual calculation, rough calculations, anything like that. So you can always check with these values given in the table itself. Similarly, this table is prepared for beams where they are predominantly bending moment carrying members. So here you will see that for beams the axial forces are 0, but you only get shear force in one direction, and there is a little bit of torsion and there is bending moment. So mainly it is the bending moment in beam that you have to consider, some torsion that is generated and so on. Similarly, if you have got the shear wall, then you have got this shear wall forces, shears in both directions, some torsion, some bending moment. In the plane of the shear wall, the moment is very large, if you see 151 or something like that. So large moments are there in one direction, in the other direction moments are less, because it has got lesser moment of inertia in the other direction. And similarly you get slap forces in ETAB 19, I think what you are considering, you are able to get those slap forces. So per slab panel that you are considering, it will give you maximum force, moment per meter width and so on and so forth. That later on it will use for design purpose. So you can see that all these output results are available for your scrutiny. Likewise you can consider the base reactions, okay, total base reaction, total load that you are applying on the buildings. It is sometimes a parameter, and an experienced engineer will roughly calculate per square meter how much load you have applied, and then he will come to a conclusion, or it is reasonable, or whether there is some gross mistake has occurred, something like that. So on an overall grand scale, whether any mistake has occurred, so those can the conclusions can be drawn considering this total reaction. Individually whether a reaction is large or small, that is very difficult to decide. But on a gross level, on the entire building, have you applied a load which is far more than normally expected in the building? So you know the total floor area, you know that now the total reaction in vertical direction. So you can say, okay, per square meter I have applied, let us say 2 ton per square meter. But if you get a figure 10 ton per square meter per floor that you are applying, then you realize, oh, this is absurd. You can't apply such large load. Perhaps somewhere your data is erroneous, and that has resulted into such gross load applied on the given structure, and so on. Likewise, whatever input that you have given, so it will give you the results accordingly. Whatever material that you have selected, I mean your data is only reflected in the output. So each of the material that you are selecting, so for different grades of concrete that you have used, or steel that you have used, so depending on that it will give you the relevant properties and so on. I think with this we should conclude for the day, and the design part, design of individual elements, we will see in next lecture, that how these individual designs are carried out, and what to expect, what is presented in the ETABS, and what is the meaning of various parameters which are displayed there, and so on and so forth. I think with this we come to the conclusion.